Welcome to the second part of this XPS and overview lecture. So, in the second part, we will talk about the instrumentation of the XPS and the data analysis, that how can we record the data and what different softwares can be used. And we will take some basic examples from lab to journal how that will help you to understand more about the data presentation. So let us come to discuss about the instrumentation. So in this section of XPS and overview lecture, we will talk about the instrumentation of the XPS. In this instrumentation, first we will talk about the X-ray sources of XPS, what different sources are nowadays using in the X-ray photoelectron spectroscopic systems, and then all these XPS systems need ultra high vacuum UHV. So what is the need of the UHV and how can we achieve this in the real systems is discussed in this ultra high vacuum content. And then later on we will see about electron lenses, energy analyzer of XPS, and detectors and monitors and recorders. So this is a schematic idea. This image is taken from the Thermo Fisher Scientific XPS Nexa Z2 model manual, and this instrumentation gives us the idea of the different components or different parts of the XPS. So this is what a camera here, a light source and camera, which actually gives us the image of the sample on our monitor, and here is what the sample mounted on this sample holder. This is sample holder, and your sample is mounted somewhere here, and this is flood gun. Flood gun, as we have already discussed, that the this is used to neutralize the charging effect of the sample, and this continuously bombard the low energetic electrons to the sample for any charging effects, nullify the charging effects, and this is very essential or crucial when our samples are not conducting. So for insulating samples, it plays a very crucial role. And here is what our X-ray source, and this X-ray source emits X-rays, and these X-rays are not monochromatic in nature. So here we use monochromators, and after this monochromator, these X-rays are sent and reflected to the sample surface, and when X-rays are falls on the sample surface, they eject electrons, and these ejected electrons uh, are uh, are making beam and accelerated through this electron lens assembly to the this analyzer, and the at the another end of the analyzer there are what detectors to detect the kinetic energy or binding energy of the coming out electrons. And here is what ion gun. Simply, the ion gun is used for the two purposes: to remove the surface contamination on the sample, and for the thin film assemblies, or to getting the information from the in-depth uh, uh, of the sample. So we will discuss it on the next slides. So the flood gun. So it is the surface. If the surface is electrically insulating, then the emission of the electrons causes a positive charge to accumulate at the surface, and it causes the peaks in the spectrum to shift to higher binding energies and become distorted. So, if the sample is electrically insulated and the electrons are piling up on the, or the positive charge is piling up on the sample, then we are getting the wrong information of the binding energies of the electrons. So this is not useful. So for this reason, it is necessary to neutralize the charging effect on the surface by replenishing electrons from an external source. This stabilizes and controls the charging within a few electron volts of the neutral state. Any remaining small shift can be removed after data collection using the spectrum processing tools. So this is the role of the flood gun and the ion gun. So mainly the ion gun is used for the remove the contamination layer. Suppose that we are talking about the pure metal samples. So metals, whenever they put into the desiccator, it's okay. In the vacuum sealing, it's okay. But when we take samples out in the ambient temperature or ambient pressure or ambient conditions, they form a oxide layer over the surface of the sample, and these oxide layers uh, may have thickness of few nanometers. So since this technique, this XPS is especially a surface sensitive techniques of the few nanometers, so we are getting the wrong data when our surface is contaminated or having a contamination layer. So it is very essential to remove this contamination layer to the uh, get the true data from the surface only. So for removing this, the XPS ion gun is used to sputter material from the sample, allowing depth profiles to be obtained. And sometimes this is also used. Suppose that we are working in the thin film field, and uh, you are interested to the interface of two films, and you want to take the surface chemistry, and you are interested into the surface chemistry of the two films. Suppose that I am using a pen here. Okay, wait. Suppose that you are using this thin film assembly, and you are having the two different layers. Suppose that this is one layer, this is layer 2, and you want to observe this data from this interface, and you are interested that some physics or some chemistry is lying there and make this very interesting here. So this ion gun sputter this whole layer 1 and give you the exposure of this interface of the layer 1 and layer 2 here. So this ion gun is also used to depth profiling, particularly or precisely this system words is what depth profiling for obtaining interface data of multi-layer samples. So ion gun is used to sputter material from the sample, allowing depth profiles to be obtained. Most XPS instruments include an ion gun that produce monoatomic argon ions. So this argon ion plus ions are bombarded on the sample surface from ranging energies. A range of beam energies are usually available, typical from a few hundreds of electron volts to a few kilo electron volts, depending upon the contamination thickness of the layers and the rate of etching you would like to obtain. The XPS instruments are equipped with ion guns to perform surface etching. So X-ray sources of XPS. Usually, in recent days, the two main X-ray sources are used by the XPS systems, the AL K alpha. So these are what the characteristic uh, X-rays of the aluminum anode. So in the X-ray sources, we have discussed that X-rays can be of two types: continuous X-rays and the characteristic X-rays. So these characteristic X-rays, if we take the anode is the aluminum metal, then it will provide us the K alpha. After the monochromatize, the energy of this K alpha is what aluminum K alpha is 1486.6 electron volt. And if we use the magnesium Mg K alpha, then the energy of this is 1256.6 electron volts. So again, here what we cannot detach the electrons whose binding energy are more than 1486.6 electron volts. So sometimes we will not able to get 1s electrons of the few elements. 1s electron of the few element. We are only able to get the Al1s electron is very difficult to obtain from this, or if the Z is greater than Al, Z of this Al, then we will not able to see the 1s electron of these higher Z number elements, because the excitation energy of the source is what? If we are taking the aluminum K alpha is the source X-rays, then it can only excite 1486.6 electron volts. So in that case, how to identify the electrons and how to identify elements? So this will give rise to the not 1s, then it can be 2s, it can be 2p, it can be 3d, and so on. So by using these data, we will identify the elements and their surface chemistry. Okay, so this slide will give us the idea about the ultra high vacuum, and this is what the give us the idea about low vacuum. Low vacuum is from 10 raised to power 2 torr to 10 raised to power minus 1 torr. Medium vacuum is from 10 raised to power minus 4 to 10 raised to power minus 1 torr. High vacuum is from 10 raised to power minus 8 to 10 raised to power minus 4 torr. And the ultra high vacuum, which is the essential requirement for the XPS systems, is from 10 raised to power minus 8 to 10 raised to power minus 11 torr. So, why this ultra high vacuum is necessary to operate this XPS? It is essential for remove the absorbed gases from the samples. Sometimes sample may absorb some gases, and by having this ultra high vacuum, these absorbed gases are coming out and taken out of the system. Eliminate adsorption of contaminants on the sample. Prevent arcing and high voltage breakdown. It is also necessary. Sometimes, since we are using high voltage in the X-ray generation and to electron detector, so for having the good ultra high vacuum prevents us from arcing and high voltage breakdown. And the last one is very important again, since the electron is what? And a charged particle, and charged particles dissipates their energies in the medium when they traverse through it. So electron, if there is no ultra high vacuum, or if the medium is there, then electron loses its energy before reaching to the detector. So we are getting the wrong information in that particular case. Wrong information of the kinetic energy and wrong information of the associated binding energy. So to getting the precise and right informations, it is very necessary to have the ultra high vacuum, and this increase the mean free path of the electrons, ions, and photons in the analysis chamber. And okay, for the comparison purpose, how can we achieve this ultra high vacuum? So here I am listed the three different types of the pumps used in the usual XPS systems, and here is the vacuum order obtained by them. The scroll pump will take us to the 10 to the power minus 3 millibar, and then the turbomolecular pump TMP will lead us to the 10 to the power minus 11 to 10 to the power minus 9 millibar, and this ion sputter pump lead us to the 10 to the power minus 11 millibar. So these are the different assemblies which actually provides the ultra high vacuum and the basic vacuum units. So this will give us the idea again to correlate the different units of the pressures. So 1 atmospheric pressure is almost equal to 1 bar, and this is equal to 10 to the power 5 Pascal. And this 1 Pascal is what? A 1 Newton per meter square, a MKS unit of pressure. And this 1 atmosphere is also equal to 760 mm of height of Hg column, mercury column. And this 1 torr unit is equal to 1 by 760 times of atmospheric pressure, and that is what equal to almost equal to 133 Pascal. And this 1 torr is equal to 10 to the power minus 3 bar or 1 millibar. So sometimes it is using torr, sometimes it is using millibar. So by this slide, I would like to clear the different units here. Okay, so electron lenses and energy analyzers. So this slide actually again briefly schematically gives us the idea that here is our sample, and here is our X-ray source, and X-ray source gives X-rays, falls on this sample surface, and electrons are emitted out. So electron optics or electron lenses are what? They are used to focus the electrons in a beam, and they are used to accelerate the electrons in the particular direction. So electrons are emitted in the this whole region, but they are what bound to move in this particular direction by using these lenses. Uh, um, these lens, because they are using the electrons for the focus. So by taking that term from the optics, we are using them electron lenses, but there is nothing like the optical lenses here. They are what electric fields applied on on these electrons. Okay, when these electrons are entering into this energy analyzer, this energy analyzer is what actually having the two concentric spheres, the inner sphere and the outer sphere. The outer sphere will have the more negative potential in comparison to this inner sphere, and the electrons will have definite same energy, or a particular precise energy will reach to the detector assembly. Otherwise they will watch here and lose its energy here, and they will not able to reach for a particular detectors here. And these detectors are multi-channel plate electron multiplier, and the data is recorded here in the computer system and analyzer controller. So this is what again a schematic diagram of the electron lenses and energy analyzer. Okay, so the electron lenses collects and slows the ejected photoelectrons from the sample surface before entering the energy analyzer of XPS. So it will work before the uh, entering of electrons into the energy analyzer or semi-spherical energy analyzer. And then energy analyzer plays its role. It is the hemispherical sector, which consists of two concentric hemispheres with a voltage applied between them. Then detector assembly, it has multi-channel display detectors, which is equivalent to a photographic plate, allows simultaneous detection of the kinetic energy of the ejected electrons. And then we will record the data on the monitors and recorders. The high performance computer is used as the recorder or monitor, which controls voltage to the lenses and analyzer. It also produces an XPS spectrum. The XPS spectra are generated by plotting intensity versus binding energy by computers automatically. So there is what dedicated softwares on these computers who actually provide us the spectra directly from the detectors. So in this section, we are going to talk about the data collection and the data analysis. We will take some examples from lab to journals, and we will uh, know about the different names of softwares in which we can record the data or we can analyze the data. Data can be recorded into the two modes: the wide scan, which is also known as survey spectrum, and the fine scan or the high resolution scans. See, whenever we are going to take the data, first what we are going to do is we take a fast scan or a quick scan, in which from the lower energies to up to a higher possible energy. It will provide us an idea that what different elements are present in our sample. So by having the idea of the different samples, now we are going for a particular element and take a high resolution scan, means we'll provide a higher time for that scan, and these are known as fine scans. So this is a data from Lab 2 publication. This paper is published in the Ceramic International. In this paper, the title was Ca plus 2 substitution effect on the electronic structure of the CaCu3TiO4 O12 studied by electron spectroscopy for chemical analysis. So, what we were interested is we were trying to look into the effect of Ca plus 2 systematic substitution in the CaCuTiO4 O12. So CCTO sample is there, the host matrix, and then we substitute Ca plus 2. So we made these samples Ca1 plus X, Cu3 minus X, Ti4 and O12, where X is ranging systematically from 0.0 to 0.1, 0.2, 0.5 and 1. So the extreme samples are Ca2, Cu3, Cu2, Ti4, O12. So Ca and Cu, they are both varying with this X. So data analysis software are the Origin software. Nowadays, Origin is equipped very well to analyze the XPS data. It provides us different background schemes which can fit multiple peaks and so on. So this is nowadays Origin can also be utilized for the new beginners is the XPS data analysis. The CASA XPS, this is very popular software and it's very versatile and used in across the globe. And the third is Avantage by the Thermo Fisher. So the XPS systems made by the Thermo Fisher use this Avantage software for the data recording as well as for the data analysis. Okay, so this is the survey spectrum of the CCTO sample where X is 0. One second. Okay, so the CCTU sample, first we take the wide scan or the survey spectrum in which we can see that there are different elements present in our sample. You can see the different peaks associated with the different elements starting from the Ti3P, Cu3P here, Cu3S, carbon 1S, Ca2P 3 by 2 half, Ca2S, TiO and these all peaks. One question you can ask from me that from where this carbon comes in your sample because you don't have any carbon in the sample. Okay, this carbon comes from the surface contamination. When I put my sample from the ambient conditions to the ultra high vacuum of the XPS system, it it come into the contact of the ambient conditions, ambient atmospheric conditions, and a layer of the carbon or the oxides is there on my sample surface. Sometimes this carbon 1s peak is known as advantageous carbon peak. Yes, though it is a surface contamination peak, but we sometimes call it as advantageous carbon peak. Why it is so? Because this C1s peak is used for the energy referencing purpose or for the energy scale calibration purpose. So the C1s, one second, the C1s binding energy is about 284.6 electron volt. So sometimes we used this carbon peak in my sample for calibrate the energy scale. Okay, now, so this is about carbon and different elements. See oxygen present in my sample, Ti present in my sample, Cu present in my sample, and okay, all the peaks of these elements only, and there are no rest peaks. See, now we focus on the Cu. Here is what Cu2p. Here is what Cu3p, 3s and Cu3p. So if we are making the orbits of the Cu, then this is what 2p orbits, this is what 3s orbit, and this is what 3p orbit. Okay, so this is what above rule by which the electrons filled up in the atomic orbits. So this 2p is what the innermost level among all these three orbits. So the Cu2p have the greatest binding energy among these three. Okay, so the Cu3p peaks are lies in the higher binding energy region. Okay, one more thing. Then in XPS spectrum, usually a convention is there that we plot the binding energy axis in this direction is the increasing binding energy. usually we take this direction as the positive, but this direction is historically taken for the kinetic energies. So for the binding energies and kinetic energies are what reverse to each other. If the binding energy of the electron is higher, then its kinetic energy is less. So we use a reverse axis for this binding energy plot or for this XPS spectrums. Okay. See, we have discussed in our initial slides about the OJ peaks, right? And OJ peaks are what? When a X-ray knocked out an electron from an atom, then this excited energy is anyhow transferred to the outer electrons, and the outer electron get ejected. So this is what OKLL peak here is what OKLL. So this OKLL is what again I make here KL. This is what 2s 2p. This is L2 L3 and L1. So if the electron is ejected from here, then these electrons, one of these electrons can fill this vacancy and a photon can emit. But rather than happening this event, this excited energy is anyhow transferred to this electron and this electron comes out. So this is what from LL to K. So this peak is nomenclatured at KLL peak. OKLL peak. Okay. Similarly, the CUL peak, CUL peak. So these are the peaks uh, uh, ascribed to the OJ peaks in the sample. And okay, one more thing that we can see that here is what Ti2p 3 by 2 and half, Ca2p 3 by 2 and half, Cu2p half, and Cu2p 3 by 2. So there are two types of the peaks. One carbon, oxygen one has single peak, carbon one has single peak. Whether the Ti2p, Ca2p, and Cu2p have the two peaks corresponding to these electrons. So we in the next slide we will try to see the role of these J values or the total angular momentum values for that. Okay, so the C1S peak for the charge referencing and the calibration purpose. So this is what a carbon peak taken from my sample, CCTU sample, carbon advantage is carbon peak. First, this is what a single peak, okay, and having the multiple components can be fit into this peak. Why it is single peak? Since the spin orbit interaction is there, and the spin orbit interaction for the carbon 1s is what the electron is lying in the orbit s orbit, and for s the angular orbital quantum number is perfectly zero and the spin quantum number is half. So the total quantum number J value is what from L minus S to L plus S with a integral change, right? So this is what only half. J is only half. So this J will gives us the idea how many peaks are there. So this J is one only. The number of J is one, so there is a single peak. Okay, corresponding to the C1s. Okay, now the asymmetric nature of this carbon peak gives us the idea that this carbon peak can be fitted by three different peaks. The one peak head is here. In the next slides, we will also gives us the idea that how can be this fitting possible. The one peak is here. The second hump can be observed here. The second peak is here, and the third peak is clearly visible here. This one. So in my previous slides, I already discussed with you that we can also able to find out the electronic environment and the chemical states of the elements present in my sample. Similarly, this peak at the lower binding energy side can be ascribed to the C single bond C bond, whereas this middle energy peak can be ascribed to the C single bond O bond, and this higher binding energy side peak, here this one peak, can be ascribed to the C double bond O bond peak. So these all peaks are in the increasing order of the binding energies. Okay, this slide gives us the XPS fine scan spectrum of the Cu2p peaks. Copper 2p, since this time we are using we are analyzing the copper 2p electrons in the detector, and for a p orbit, the orbital angular momentum is what? Perfectly 1, and the spin quantum number for the electron is what? Half. So this time for j values, this is what? J minus s to j plus s with the integral change. So this 1 minus 1 by 2, 2 1 plus 1 by 2. So this will lead to the half and 3 by 2 different j values or 2 j values. So this spin orbital coupling or the spin orbit interaction leads us to the two different peaks. Okay, now if we draw the peaks in the increasing order of energy, then here is what? 2p half, and here is what? 2p 3 by 2, and this is what? Increasing order of energy. So 2p half is more towards the nucleus side, and 2p 3 by 2 is more away from the nucleus side. So the electrons residing here have the more binding energies, so you will get the peaks of these electrons at the higher binding energy side with comparison to these 2p 3 by 2 electrons. Similarly, you can see that these lower binding energy peaks can be ascribed to the copper 2p 3 by 2, whereas this higher binding energy peaks can be ascribed to the Cu2p half. So these different spectras are for the different doping of the Ca plus 2 in my CCTO, original CCTO sample, right? One more thing, since there are too many peaks arises in the spectrum, so how to get the precise idea that these peaks are for the copper peaks? Since there are sometimes satellite peaks, sometimes there are OJ peaks, sometimes there are background peaks, so how to identify that these are the copper peaks? So one thing, the copper peaks is almost occurred or find out at the 920 to 960. One thing. Okay, the second important thing, that the separation between these two peaks is precisely same as the 19.75 electron volt. So if there is any false peak, suppose that how this one cannot be ascribed as Cu2p half. There is peak, but they are what? Satellite peaks. So these peaks have not the particular separation of 19.75 electron volt energy. So this Cu2p half and Cu2p 3 by 2 in this spin orbit interaction having a definite energy of 19.75 electron volt, and this can again read by these two peaks or the separation of these two peaks. Okay, so this is for Ti2p peaks. Similarly, for the we studied about the copper. Similarly, for the Ti, we are having the 2p electrons. So orbital is p. So orbital angular momentum is 1, and spin angular momentum quantum number is half. Again, there are two possible j values and corresponding to two different peaks in the spectrum. So the again Ti 2p half is more inner orbit than Ti 2p 3 by 2 in the increasing energy order. So Ti 2p 3 by 2 is on the lower side and the Ti 2p half on the upper side. And since this is my oxides, the CCTU is what? Oxides, CaCu Ti4 O12. So for a particular oxides, this Ti4O12, the difference of the energies between 2p half and 2p 3 by 2 is what? 5.7 electron volt, which is found in the literature. So I again would like to confirm myself that whether these two peaks are truly correspond to the titanium 2p peaks or not. So I got the difference, and yes, the difference is same as the reported in the literature. These are the oxygen peaks. Again, I already discussed that C1s peak and oxygen 1s peak, since S electron has L equal to 0, so they are single peaks. So L equal to 0 and S equal to half, the only J value is possible half. So a single peak is there for all the oxygen peaks. And these are the four different concentrations of the Ca plus 2 from 0.2, 0.5, 1.0, and this is what increasing binding energy scale in this type. And on the y-axis, this is what intensity in arbitrary AU stands for the arbitrary units. So we are only interested arbitrary to with respect to one another. So we are going to report our data into the atomic concentration, means percentage atomic concentration, how much is the Ca, how much is the Cu, and how much is the Ti, and so on. So we are using only the arbitrary units of the intensities here. Okay, so in this way, the oxygen 1s peak have the asymmetric nature. It is not symmetrically Gaussian, which is what the Gaussian function is purely symmetric like this. But this peak is what a hump is here, again a hump is here. So this is asymmetric in nature. This asymmetricity provide us idea about the different components may fit to the this oxygen peak. So we are trying to fit different components in this oxygen peak. So this first component, we call it P1, correspond to the lattice oxygen. The lowest binding energy site component, this one is O1S XPS, correspond to this lattice oxygen. The second peak here, P2, ascribed to the oxygen defects, and the third peak here, which we call P3, is ascribed to the absorbed oxygen on the surface of the sample. And this background, and this is what the sum, the envelope, the whole sum, and this black data is for our raw data, and we fitted peaks 1, 2, 3, and the sum of these three peaks is what the sum or envelope data. And we can see that these raw data and these sum data are exactly matches to each other. Then it means that we are fitting the good values of P1, P2, and P3 in these O1S data spectrum. Okay, so in conclusion, we can say that XPS is a technique for analyzing the surface chemistry of a material, and XPS can measure the elemental compositions, can give us the idea about the different elements present in the surface. By having the different idea, we can having the concentrations, atomic concentrations, and by which we can able to find out the empirical formulas. And by XPS, we are also able to find out the chemical states and the electronic states of the elements present in our sample. So XPS spectra are obtained by irradiating a solid surface with a beam of X-rays while simultaneously measuring the kinetic energy of the electrons that are emitted from the top 1 to 10 nanometer layer of the sample surface. A photoelectron spectrum is recorded by counting ejected electrons over a range of electron kinetic energies, and peaks appear in the spectrum from atoms emitting electrons of a particular characteristic energy. And the energy and intensities of the photoelectrons peaks enable us to identification and quantification of all surface elements except hydrogen and helium. So this is all about our conclusion. And I'm happy to inform you all that recently in my department, we have procured a thermoscientific Nexa G2 surface analysis system at Department of Physics, University of Rajasthan, Jaipur, under the RUSA 2.0 funding scheme. So RUSA is what Rashtriya Uchtar Shiksha Abhiyan, provided by the Ministry of Education. And these are what different useful links and the references. So I would like to recommend these links to the newcomers and who would like to learn the XPS from the very basics and very fundamental way. So this is what Thermo Fisher XPS website is xpssimplified.com. It provides us the valuable informations, and it has a data library which provides some very good informations when you are analyzing your data. So you will frequently use it for your data reporting. And yellow books from Casa XPS. Casa XPS software also provides some basic and fundamental knowledge of XPS. And these yellow books are very good for the beginners, and they can be find at the casaxps.com in ebooks, ebooks.htm at the website. And one more important link is 5 handbook of X-ray photoelectron spectroscopy. This can be find at phi.com support reference materials and handbook HTML. These all are very reliable and very important links and references for the beginners of starting the research in the XPS field. And the acknowledgement, I would like to acknowledge my head of the department and Professor R.K. Singhal from University of Rajasthan, Jaipur, who actually taught me the analyze the data of the XPS, and my all research members of my group research group at University of Rajasthan. So this is my mail ID. So whatever you want to discuss more about this XPS, and if you find any problem in data calculation or in data recording, you can immediately mail me at JAKHARNAREN Jakhar at the gmail.com. So thank you very much. So it's all from my side, and I think that I am able to reach up to you and give you a fruitful bit of information in your future career. So I'm again, once again, would like to thanks Teacher Learning Center, Ramanujan College, University of Delhi, to provide me this great opportunity here to interact with the young entrants in the physics teaching. And I'm again really thankful to you all audience which are here with me and bear me for throughout these sessions. Okay, thank you very much.